Bam! Mr. Tarrou. In this math lesson, we're going to be looking at the basic operations with geometric vectors. In other words, sketching the resultant vector we get from adding and subtracting multiple vectors, dealing with scalar multiplication, so on and so on. In the description, you will find timestamps to the different examples we do in this video. There's going to be about, I think, like around 5. You'll also find a link to the playlist that will have all of my vectors that I've done to date, and of course that'll keep growing as I make more and more math lessons for us. So we are going to find the right page. Yeah, well, I gave you a quick rundown. Let's just get to it. We're going to be adding vectors two ways. The more restrictive process of graphing the sum of two vectors is the parallelogram law, and it is good for a couple of vectors with different directions that also share the same initial point. So our example here is going to be sketch the geometric representation of vector AB plus vector AD. Now we know these are going in different directions because the terminal point for each of these vectors is, well, represented by a different variable, and the initial point of both of these vectors are this point A. So we do indeed have two vectors with different directions that share that same initial point. Parallelogram law. So now what you do is you draw your two vectors that are sharing that same initial point, and then the best you can, but give a reasonable representation of a, well, parallelogram, so your opposite sides are equal and parallel. And then we're going to just simply connect the dots. We're going to go from the initial point that these two vectors share, and we'll pick yellow here, hopefully it stands out on the camera, and then go diagonally through the parallelogram. Try to hit your point though, a little better than I did. There we go. And that new vector, this yellow vector, with that still that initial point of A, now coming out here to what? Let's see, we have A, we've used, oh, and where would these coordinates be actually? I meant to do that. I left this unlabeled for a reason. If I call this vector AB, and since we're just being introduced to vectors, you know, which of these points is A? Is this A or is this A? Well, this notation above the letters of A and B indicate, well, the arrow, sort of that visual representation of that vector, is starting at A, which is indicating and ending the point of that arrow is above B, indicating that point B is the terminal point. So this is point A, this is point B, this is point A, or vertex, if you will, of the parallelogram. Now we have a terminal point D, and since I've already used A, B, and D, how about we just call it C? So this yellow vector, this is the resultant of doing, well, AB plus AD. Vector AB plus vector AD. And since now I've added another letter to my diagram, I could also say that it's equal to vector AC, but that is the resultant vector. Well, that's great. Let's keep going. How about vector AD? We're going to sketch, right? We're not doing mathematics yet. We are not looking at these vectors analytically yet. We're just going to sketch AD plus AD. Vector AD plus vector AD. Well, if the only technique I have for sketching these resultant vectors is the parallelogram law, I'm not gonna, they're supposed to have the same initial point. So, I mean, is it vector AD and vector AD? That's not actually correct. We have vector AB. Okay, so sketching what AB looks like over here, kind of about this long and going up in a sort of that direction. If I'm going to draw a parallelogram, the parallelogram law is good for when the two vectors share the same initial point. Well, B is the initial point of this vector, and yeah, B to C. Now I know that we just added, I'm referring back to this previous diagram, that C is kind of like over here horizontally. The terminal point C is horizontal from the initial point of B. Now, if this is a parallelogram, vector BC and vector AD are the same vector, but if I start with this expression, you know, what's vector AB plus vector BC, without this initial expanding on this idea, I don't really know what vector BC looks like, and I don't necessarily know that vector BC is equal to vector AD. So we need a different technique, and I'm showing it's sort of like end to tail. It's called the triangular method. When you have a couple of vectors that do not share the same initial point or do not go in different directions, you're not able to, well, set up a parallelogram and then just draw through the diagonals or connect the diagonals. No, you go, okay, this is the first vector, I'm going to go in this direction. Now the second vector starts where the first vector ended. This initial point is the same as this terminal point. We'll just connect it end to end, the triangular method. And then when you get done connecting end to end the 2 or even 3 or 4 vectors, multiple forces now, not just limited to 2 like we are with the parallelogram method, you can go back to your first initial point, your final terminal point, connect the dots, go from initial to terminal, and this, using the triangular method, is the resultant vector AB plus BC. And if I'm looking back up here at my first example, AD, vector AD plus another vector AD, right? When you sketch a vector, but the initial point does not define the vector, it's the magnitude and the direction. So if I say this is AD and I want to add it with another AD, I just tack on another AD right here, and this is the resultant vector. Actually, AD plus AD is simply nothing more than 2AD, almost like you're adding like terms. And I'm leaving. Alrighty then. Properties of vector addition. We have the commutative property that vector u plus vector v is equal to vector v plus vector u. Okay, so it doesn't matter the sequence in which we do that addition. Well, let's see here. Vector u, which I've got going down 3 units. We're going to do triangular method, plus v up to and over right. So up to over right, 1, 2, 3, 4, 5. This is u plus v, a vector that goes to the right 1, 2, 3, 4, 5, and down 1, kind of hinting towards the analytical method of analyzing vectors. This is supposed to be just geometry, but need a little better visual aid than just saying these work because I say so. Vector v plus vector u. So it doesn't matter. Okay, so if I do v first, so if I do vector v first, up to over 5, so from this initial point up to 1, 2, 3, 4, 5. Next section we're going to be talking about representing vectors analytically with their horizontal and vertical components. That's what the graph paper is doing here, besides giving me a more accurate picture, preluding to. Vector u is down 3, so down 3, 1, 2, 3. So here's vector v, here's vector u. Connect the initial point with the terminal point. Here we're looking at vector v plus u. Well, look here, so we have 2 resultant vectors, u plus v, v plus u, both in the same direction and same length. And in their component form, 1, 2, 3, 4, 5 over, 1 down, 1, 2, 3, 4, 5 over, 1 down. Now the associative property says that if you take this vector uvw, uvw, that doesn't matter the order in which you do the addition. You can do the first 2 first or the second 2 first and kind of group those additions together, just like with our normal associative property for additions. Let's see if we can't do this really quick here. We have v, u plus v. We already know what that looks like. So if I do that addition first, okay, so that's my resultant for my sum of u and v, vector u and v. Now if I add in w, which is to the left 2 spaces, so if I go back, oh, this is going to be a little bit of an ugly picture here. So this is w. Our resultant here of doing, or my sum of u plus v plus w is a vector. First initial point, last terminal point. So I end up with a These are just examples, of course. This isn't like a proof or anything. But I have a vector that's going to the right 3 and down 1. Now it says here, if I take, first I have to do vector v plus w. Okay, so let's run out of colors here in orange. Vector v plus w. V, which is up 2 over 5, right? Up 2 over 5. Vector v. W is back 2. Yellow for the final answer. Start at the initial point, end at the final terminal point. Okay. Now, let's see. The right side of this identity. Start with vector u, which is going down 3, and add with it the sum of v plus w. Well, v plus w is a vector that goes up 2 and over 3. So from this terminal point, up 2 over 3, and we have got a final resultant, first initial point, final terminal point of u, vector u, plus the sum of vector v plus vector w. Now this again is not a proof, but just as an example of what's going on here, we have our final resultant, the left side and the right-hand side of this associative property has a vector, at least with this specific example, that goes over 3 down 1, over 3 down 1. So it's an example of this property in play. Now, remember your zero vector, your trivial vector, your null vector. If I take some vector and add 0 to it, or 0 plus that same vector, I'm just going to get vector u. If you add a trivial vector or null vector, it doesn't change anything. You're right back to where you started from. And your additive inverse, vector u, or any vector for that matter, plus its negative vector or its opposite vector is going to, regardless of the order, is going to give you a null vector. So if you say, if I take vector u, which is down 3, and then I add with it the opposite vector, which is going to be, now how do I show this? What's negative vector u? What's the opposite vector look like? I can start at this terminal point and head right back, instead of down 3, up 3, and get right back to where I started from. Or maybe I could say the initial point does not define a vector, it's its direction and magnitude. Maybe I could put the initial point here and go up 3, and we're just at a point. So I kind of like this better. Initial point u, opposite of u, go backwards. I'm back at the initial point, and I haven't been displaced at all, a distance of 0 from my initial point. Scalar multiplication, the product of a vector u and a positive scalar k is another vector v with the same direction as u, and the magnitude of this new vector is simply the scalar of the original. Now what the heck does all that mean? It means nothing more than what you saw in the previous scene. Vector AD plus vector AD is simply a new vector, whether you call it 2AD or introduce another vector, maybe say that maybe vector BC is equal to AB and connect it all together and say it's vector AC. But basically it's this. Look, if I want to squeeze in a tiny bit of room here that I have left, if I want to show representation of 2w, I'm applying the scalar multiple of 2 to vector w. Just go in the same direction, but go twice as far, go twice as long. So instead of 2 units to the left, we're going to go 4 units to the left. And this is vector 2 times w, 2 times vector. That's that. We'll just write up, and I'll probably just go to another screen. In general, the product of a vector u and a negative scalar, just kind of like the idea of a scalar, but what if it's negative? I'll just write that up, let you read it, take a note, erase it, and we'll start going through our examples next. Okay, I was just going to breeze over this, and then I thought, this kind of sounds as clear as mud. In general, the product of a vector u and a negative scalar k is another vector v with the opposite direction to vector u and magnitude, which is equal to, right, these absolute values, sort of looking things, but in vector notation means, let's find the length of this vector. The magnitude of vector v is equal to the absolute value of k, right, because our scalar is multiple, times the magnitude of vector u, but then to indicate the fact that you multiply by a negative scalar, you've got to keep this negative out here indicating that it's in the opposite direction. That negative times the magnitude of k, the scalar multiple k, times vector u. So what the heck? It makes it sound way more complicated than it is. So going back to the previous couple of screens here, we have vector AB plus vector AB is equal to, well, simply another vector which is twice as long. Vector AB, triangular method process, plus another vector AB. But now this is going to get a little bit convoluted because let's call that vector AC, a new vector that in terms of a positive scalar multiple goes in the same direction as the original vectors. So vector AC, so we're going to let that vector AB, we're going to introduce sort of another vector, if you will, and say the vector BC is equal to vector AB. And so we have this new vector AC, which is twice as long as vector AB because we have that scalar multiple of 2 that goes in the same direction. So with that sort of diagram and that idea that AB is this length going to the right, negative 2 times AB is equal to, well, that scalar multiple is going to come out, and that is 2 times the opposite of vector AB, the opposite vector or the opposite vector. So like, in other words, if this is A and this is B, we want to go in the opposite direction. So in other words, the opposite of vector AB is actually BA. So instead of starting at A and going to the terminal point of B, this opposite notation means that we're going to go from point B to point A and have this opposite vector really be vector BA. And now we're going to move 2 of those distances. And let's just for convenience call this, well, it's sort of weird now because this is AB and this is also another, excuse me, this is vector BA and this is another vector BA, but we have this new vector of CA, this new vector which is twice the length of the original vector, but see, we're going in an opposite direction. Instead of the opposite of AB, we're going to relabel that as BA instead of the opposite of AB, in case I just misspoke there for a little bit. So it all sounds really complicated, but like you saw me do on the graph paper, if I have this vector going this way and this is vector V, and I want negative 2 vector V, just go in the opposite direction. Instead of to the right, go to the left, but go 2 of those spaces. And this is negative 2 times vector V if this is the original vector V. And then we can call that, if need be, give it another vector name to make it easier to differentiate this vector from this vector. So we have the properties of scalar multiplication, very similar to your addition. With scalar multiplication, we have the commutative property, the associative property, the distributive property, just like you would expect, even just working with some basic algebra, where you have a scalar multiple going into the sum of 2 vectors. And if you've already added 2 scalars, you can apply that to the multiplication of that vector. For some reason, if you need to do the vector V times the first scalar, and vector V then times a second scalar. In the previous screen, we said, scalar multiple k, but a lot of times in these advanced mathematics books, you might see these scalar variables represented with the Greek variable. So at any rate, this is just an extension of what we started on the previous page. In white, we're going to take a look at, given vector A, B, and C, what does 2A minus vector C look like? Well, we have a scalar multiple of 2 applied to A, so it's just going to go up instead of 2, sort of a distance of 2, it's going to go up a distance of 4. And minus C, well, I just see that I got myself in trouble because C goes down and to the left, down 3 and over 1. Well, the opposite of C is telling me that instead of going down 3 and over, we're going to have to go in that opposite direction or kind of rotate this 180 degrees and go over 1 instead of to the right instead of to the left. Instead of down, we have to go up. So we're going to go, well, let's see, what do I want to do? Let's just write over this. We'll just move this name over here. And instead of down and to the left, we're going to go to the right and up. This is the opposite vector to C. And this is what the resultant looks like. Here's your initial point, your last terminal point, and there is 2 times vector A minus vector C. Now, in green, let's take a look at negative 2A plus 1/2 B. So we have a negative scalar and a positive scalar. One's going to make this is going to make that vector twice as long, but in the opposite direction. So negative 2A, instead of going up 2, is going to go down because of the negative scalar. And we're going to go twice as far. So we're going to go, let's see, not down, not the opposite direction of A, but twice as far. So instead of up 2, down 4. So then we have negative 2A. We're going to add that in the triangular method, 1/2 of B. So take vector B, which is 1, 2, 3, 4, 5 units long, reduce that or multiply it by a factor of 1/2, so it's 2.5. So we have 2.5 in the same direction because it's a positive scalar. Adding these triangular method, initial point, last terminal point. And this is a geometric representation of negative 2 times vector A plus 1/2 vector B. Now, lastly, this really highlights why we need to look at this triangular method of adding vectors, at least, a graphical sketch. You're not going to make a parallelogram out of 3 different vectors, but vector A is a vector going up 2, and then we have vector B, this initial point on that terminal point, right 5, vector B, and then finally vector C is down 3 over 1. So from this initial point going on this terminal point, down 3 over 1, and that is the addition of vector C. These are all positive, so all are going in the same direction, not the opposite direction. And this is the graphical representation of vector A plus vector B plus vector C. Now we're going to take a look at more examples, just becoming with increasing difficulty that you may see in your book. These are also coming or being inspired by some problems in my HL Math book and for IB, so they may be a little bit more advanced than you might see in your class, maybe not, I'm not sure, but either way, they are interesting. Bam! We're going to take this regular hexagon A, B, C, D, E, F, and using only using only vectors defined by vertices of the regular hexagon, complete these statements. I want to rewrite 1/2 FC plus DC. Okay, so 1/2 FC. Well, vector FC goes, through sort of like a diagonal of this regular hexagon, passing through the origin. Now, 1/2 FC would be FO, except O is not a vertice or vertex of this hexagon. So that means that I need to use or name a vector using the vertices of this hexagon that is the same length and in the same direction as vector FO. Well, that means I can either say it's 1/2 of FC is either AB or ED. Okay, so we're looking at either vector AB or ED. But then what are we doing with that? Both of these vectors, same length, same direction as FO, and using the vertices of the hexagon. But then we want to add DC. Well, if I go AB and I add to it a vector DC, a vector that's going up to the right, I'm going up to the right out in the middle of nowhere, not landing on another vertex of the hexagon. So that's why AB in this particular case, not because it's not equal, an equal vector to 1/2 of FC, but simply once I add DC to it, this vector going up to the right, I won't be on the hexagon, hexagon anymore. So we're going to look at 1/2 FC is going to be vector ED. And then with that, we're going to add to it vector DC. So if I go from ED, now to that vector ED, add DC, I can name a new vector that only uses vertices that are on this hexagon as directed. And we're going from initial point E to final terminal point C, and this is vector EC. So with that example, maybe you can pause the video and give that second one, a shot. So let's see what we got here. We want to start off with a vector that's twice as long as FE, but goes in the opposite direction. Well, FE goes down to the right. We want to go in the opposite direction, which is sort of up to the left. I want a vector that's twice as long. Well, those diagonals, you can prove that. My previous video, I talked about properties of hexagons, and ultimately we got to where each of these triangles, these subdivisions, are equilateral triangles. So, and I'm not going to bother reproving that, but these are equilateral triangles. So this is one side of an equilateral triangle. All of these triangles are congruent, and AD, vector AD, is going to be made up of two of those line segments that are, or two vectors, that are the same length as FE. So, -2 FE is equal to vector DA. So yes, we're not going to have a vector that is a side of the hexagon, but that wasn't the directions. The directions were defined vectors using the vertices of the hexagon. So -2 vector FE is now vector DA. Now to that, we want to subtract BA. Okay, well, if I go D to A and subtract BA, well, BA is going from right to left, but that's a negative or opposite vector. So actually what I can do is just say, well, okay, you want to go to the opposite of vector BA, then add to it vector AB. Don't go in the don't have, we're going to change the negative to a positive. We're going to use an opposite. You could write it like this if you want. Minus the opposite of vector BA is AB, just to show that middle step. So we go from, again, vector, a new vector, twice as long as FE, vector FE in the opposite direction, so DA. We're now here. We're going to then subtract BA, or subtract the opposite of vector BA, which is add vector AB. So BA, B to A, but in the opposite direction, so A to B. And then to that, add vector BC. Okay, well, let's see what we got. Go to D to A. Now add vector A to B, or vector AB, and then add to that vector BC. So we're here, to there, to there, to there, and this is the resultant. The resultant is vector. So it can be, you have to put a little bit of thought into some of these questions where you're just doing vectors, but geometrically, the easier way, without getting all the fancy math. Yet it still can be a little bit confusing, especially the second part here with A number 2. So example here, we're given a parallelepiped, A, B, C, D, E, F, G, H. And here we have it drawn. It just means each of the faces are parallelograms. And we're going to let U, let's color code this. We're going to let vector U be BF. We're going to let vector V be BC. And then, nice three-dimensional drawing here hopefully will help. We're going to let vector W be equal to vector BH. So vector W is starting at B. Is that going to show up enough? I'll use blue. start at vertice B and go down into the back lower corner. So we're going from the upper left corner to the back lower right corner of this. And I'm not going to dot this just to try and make it clear. Sorry that there's so much, these two vectors are getting pretty close to each other. Okay, so we have vector U going from front left to right front left. We have vector V going from left front upper to left rear upper part of the box. Vector W, upper front left to lower rear right. Try and get that three-dimensional as much as we can on a flat chalkboard, help you see that. Now, express each vector in terms of either U, V, or W. Vector U, vector V, vector W. Okay, so vector B, G. How do I get from the front left-hand, upper left-hand corner to the upper right rear corner? This one's, give it some thought. Look at this picture. We have a red vector going front to back on the upper part of this parallelepiped, and a green vector moving to the right, staying both front left, front right. Well, if I start at B and go back to vertex C through vector D, and now, right, initial point does not define a vector, it's just simply direction and magnitude. So I can say, well, this vector BF or vector U can start from any point. So, and since parallelograms have opposite sides which are equal length and same direction, vector CG will be the same as vector BF, or basically, if this can be represented as vector U, then this back can be represented, again, by vector U. So vector BG is the sum of vector V. Well, I guess I don't need to color code it now. Plus vector U. Now this last example, or question we're being asked, write vector AG as some kind of sum of vector U, V, W. Maybe you need all three, maybe you don't. And this one's a bit of a challenge because we have a vector W which goes from the top of this parallelepiped to the bottom, but we actually need to go in the opposite direction. We need to go from A to G. We need to go from the bottom of this parallelepiped to the top. So we actually don't want to go from top to bottom. We want to go in the opposite direction. So the first thing is, I'm going to need to erase part of this board. And you may see this differently than I do. I know my students last year with a similar question got equivalent answers by visualizing the diagram differently than I did. So you play around with this question while I draw a diagram. Now, I'm going to do my best to try and help you see this 3D representation, but again, the way I see myself moving through this space may not be the same as yours. But I'm going to start this off with, instead of going top to bottom, we are clearly going to need to move from A to G, from bottom to top. So I'm just going to simply start this with a negative vector W. So that means that, and keep in mind, by the way, this is a good idea. I need vector AG. I need, ultimately when we're done, a vector that goes from the front lower corner up to the back upper right-hand corner. And my resultant doesn't need to be in this position. It just needs to be in this sort of orientation or angle with that direction. So if I say we're going to start with negative vector w, which I labeled initially with blue, instead of B to H, we're going to move from H to B in an opposite direction. Okay. Well, that's all fine and dandy, but I need to do a triangular method for adding vectors, and in the end, connect the first initial point with the final terminal point. And so this A is like my H right now. I need to go right, back, and up, basically one corresponding length of that parallelepiped. But right now, I'm not to the right and up. I'm somewhere forward, left, and up. So I need to basically figure out how am I going to get a vector that doesn't go forward and up, but goes backwards and up. This is my initial point. Now I'm here. Okay, well, I can only move with vertices of this parallelepiped. So what I'm going to do is I'm going to extend this diagram. I'm not sure if I'm going to make this dotted or solid. I guess I'm going to do it dotted, or solid, I mean. Okay, the yellow one is the original one, right? I had a vector going from the front left down to the lower right. I need to go in the opposite direction to get that movement up, like we have for A going up to vertex G. Well, if I sort of transpose this yellow parallelepiped back here in the back right-hand corner, I want to go from this front lower left corner to the up rear right corner. Well, I went from H to B. I need to get back over here. Okay. Well, with the expansion of this diagram, I hope it's not too complicated for you now. We're going to go to the right 2 lengths, horizontal lengths of the parallelepiped. We're going to go to the right, not 1 vector of U from B to F, but 2 of them. And then we need to get to this back right-hand corner. So ultimately, after I move all these vectors, multiple scalar multiples of u, v, and w, I go from this H, or for this back parallelepiped, what would be vertex A, to vertex G. Well, H to B, over to, back to, going back 2 vectors. Now, not actually back, right? Because vector V went from the front to the rear, up to the right, if you will, and we want to go from the front to the rear. So we're going to actually move in the same direction as this vector V. It's just that we need to move 2 of those. And that is the answer to our third example. Is it the only way you can see your way through the problem? No. But, and maybe you have plus 2u, minus w, vector w, plus 2 times vector v. You can move these around as long as you keep the signs with them, but that is how you visualize your way through this particular fairly difficult geometric vector problem. No. And here for our last 2 examples, we're actually going to maybe get a little bit simpler for these last 2 than that previous example, as long as you remember a little bit of trig, or your law of either sine or cosine. Given this parallelepiped again, we're going to be given the fact that BF is equal to 5. BC has the magnitude of vector BC has a value, or is 2. And the magnitude of vector BG is equal to, okay, with all that then, find the angle of BFG. Or in other words, your book may just have a little m here, the measure of angle BFG. Okay, Well, I have the magnitude of vector BF, the magnitude of vector BC, and the magnitude of vector BG. But really, there's vector notation, but you're just being given the sides of a triangle. Because if you focus right here, remember this is a parallelepiped, the opposite sides are equal. All the faces are parallelograms. The opposite sides of those parallelograms are equal. If this is a length of 2, then vector FG also has a length of 2. So you're just looking at a triangle that has a side of 5, a side of 2, and a side of 6, and we have B, F, and G. It's really helpful for me to take the visuals out of these diagrams sometimes and just simplify it. Yeah, if you are finding the missing angle of a triangle when you know all three sides, you're working through the law of cosine. If you know a side and if you have a pair of where you know a side and its opposite angle, then you're more likely going to be using the law of sine, not the law of cosine. Okay, so we want to find angle BFG. We're going to start that with the side opposite that unknown angle, so 6 squared. Okay, a side squared is equal to the sum of the two other sides squared minus 2 times those other two sides times the cosine of the angle opposite that given side. And you're just simply going to work through this, subtract both sides by your 5 squared and your 25. So we're looking at F is equal to the inverse cosine. I'm going to turn this around too. 6 squared is 36, minus 5 squared is 25, minus 2 squared, because we're moving the 5 squared and the 2 squared over, which is going to be minus 4. Subtract those over, divide by negative 2, times 2 is negative 4, times 5 is negative 20. And that, right off the top of my head, now I just dropped to one letter naming of the angle because I pulled this triangle out to the side. That's not very good though, because there's all kinds of angles coming off of that vertex there. So the measure of angle BFG, right off the top of my head, is equal to 110.487 degrees. And don't round this off too soon. Put this in exact format, or your negative 7 over 20, into the inverse cosine function. Don't round off until you get to your final answer, and then you can round off to 3 decimal places. Now, our last example used the properties of vector addition and scalar multiplication to solve the equation for x. And so far, our properties of vector addition and scalar multiplication look very similar to just properties of addition and multiplication. So solving this is going to look like we're just solving an equation. But this is a scalar multiple to the difference of two vectors, or x plus the opposite vector of u. And one of those properties said that we could just multiply or distribute through that scalar multiple. So we have 3 times vector x minus 3 times vector u plus, same here with the 4 times vector u minus 4 times vector v. Well, when you're looking at this vector notation, one of the properties for the addition of vectors allows you to just sort of add those scalars. So negative 3 plus 4 is 1. There yet. We're going to move everything over with the opposite of the addition of vector u is to subtract it. The opposite of the subtraction of 4 times vector v is to add it. So we have 3 times vector x is equal to 4 times vector v minus vector u. And vector x, after we multiply both sides or distribute a scalar factor of 1/3, we get vector x is equal to 4/3 vector v minus 1/3 vector u. And that is hopefully not more than you needed for your class. If so, maybe you just stopped already, or you just continued through this lesson, to fill your curiosity. But for my homework, for basic operations of geometric vectors, these are all the examples my kids are going to need to finish their homework. Hopefully it works for you too. I'm Mr. True. Bam! Go do your homework.